Okay, today's video is Pearson EdXL Physics Linear A-Level. It's the paper 2 in year 13, so it's Advanced Physics 2. So it's the equivalent in International EdXL of IAL Unit 5. Yeah, so if you're doing IAL Unit 5, which is on fields, particle physics, and that unit is very useful. The difference with the paper 2 for the linear compared to the modular is that in the linear in year 13 they also need to revise year 12 stuff. So if you're also repeating some units for year 12, for example, waves, this unit will be very handy, okay? So I think it's waves and materials that's is linked with the unit 5. So basically in the linear, they do all the same year 13 stuff as in International A-Level. And they also do 2 of the topics from year 12, okay? So it's worthwhile looking at this if you're revising for year 12 and you're doing International A-Level as well. Okay, so it's kind of unit 5 with a bit of unit 2 and I think materials. We'll have a look. Okay, all right, so let's go straight into it. I gave this as a mock to them. I've got some linear students and I've got some International A-Level students. So here we have a Hertzsprung-Russell diagram, yeah, for stars in our galaxy. As shown, so for stars in our galaxy is shown V, W, X, Y, and Z are positions on the diagram. Okay, so what is the Hertzsprung-Russell diagram? It's got luminosity on the y-axis. Okay, so as you go upwards, it's more luminous, and temperature on the x-axis, and you'll notice that the temperature is non-linear. Okay, both of the scales are non-linear. Yeah, you'll see it's powers of 10 for the luminosity. So they go up from 3,000, then 6,000, then 12,000, and 24,000 Kelvin. So it keeps doubling as you go to the left on this scale. Okay. Now, what you've got to know about the Hertzsprung-Russell diagram is that 1 represents the luminosity of our sun, and our sun is also around 6,000 Kelvin. Okay, so our sun would be where the 1 meets about 6,000. And this curve, let's do it in a different color again, this curve here is the main sequence line. Okay, so this is the main sequence stars where they're fusing hydrogen into helium. Okay, and then you've got to know the rest of it. And it says, the question is, which of the following gives a sequence of positions of the sun during its lifetime? Okay, so the sun is currently where I've put a luminosity of 1, about 6,000 Kelvin surface temperature. Okay, and our sun is therefore going from the main sequence, which is X, closest to X, you can see, so closest to where I was showing you where the sun would be, to W, where it would go into its red giant phase. And then when it runs out of fuel completely, it'll then become a white dwarf, which is where white is. Okay, so Y is white dwarf, W is a red giant, and X is now, which is the main sequence phase of hydrogen fusion. So the answer is B. That was a bit long-winded, but I think Hertzsprung-Russell diagrams are a very common question, so you need to understand what the different parts of it indicate. Question 2, a satellite of mass m orbits the Earth with a speed v. So this is in further mechanics circular motion. Okay, you can see I've also put which IAL unit is from. The first one was Unit 5. Question 1, this is also IAL, International A-Level Unit 5. So you've got to work out what is the speed of the satellite of mass 2m orbiting at the same distance from the Earth as the satellite of mass m. So they're comparing a satellite of mass m with a satellite of mass 2m. Yeah. If the first one has a speed v, what will be the speed of the one which is 2m? So we know that for circular motion, the acceleration will be mv squared over the force, centripetal force will be mv squared over r, and the force is due to gravitation, so it's gmm over r squared. The little m's cancel out, so it makes no difference what the m is. So as I've put here, v is not dependent on m. Yeah, they mean the mass of the satellite. It's only how far away you are from the satellite, which affects it. So the answer is B. Okay. So you can see how the m's cancel out. So m is irrelevant to the speed. Okay. The next question is about an isotope, francium. Okay. Undergoes a series of alpha and beta decays before forming isotope of tellurium, I think it is. Yeah. So again, this is a Unit 5 question. Which row of the table shows the number of alpha particles and beta particles emitted during these decays? Yeah, so the subsequent decays. So alpha, you need to know that alpha reduces the mass by 4, and the mass has gone from 221 to 205. So that's a reduction of 16. So it's going to be 4 alpha, because beta does not change the mass. The beta doesn't change the mass. So you know it's going to be C or D, because what a beta does, it changes one of the protons into a neutron. So the mass in the nucleus stays the same, because proton and neutrons both add to the top number. But what's going to happen is that if you've had 4 alpha decays, you should have lost 8 from the bottom, so it should be 87 to 79. Yeah, that will be 8 of them, 4 times 2, but you've actually got 81. And what beta does, it changes. Actually, I've done this wrong. It changes a neutron into a proton, so it increases the proton by 2. So this bit is incorrect. This bit is incorrect. It's a neutron in beta, which splits into a proton plus an electron. Okay, that's what I should have written. And that will make the proton number go up from 79 to 81. So you get the bottom number correct as well. Yeah. So it'll increase the proton number by 2. Okay. So the answer is C. So you want 4 and 2. Okay, question 4. It's an electron diffraction experiment. So this is not from Unit 5. This is from Year 12, International A-Level Students, Unit 2. Okay, so electrons, so for electron diffraction, electrons are accelerated by a potential difference, okay, between a hot filament and an anode. Okay, that's called thermionic emission, and the anode then is positive, so it accelerates the negative electrons. An electron beam is produced, and that strikes a sample of a crystalline material, causing a diffraction pattern. Okay, so basically the crystalline structure of the material acts like a diffraction grating. So the diffraction grating equation from Year 12, you should remember, is n lambda equals d sine theta. And they want you to know which of the following would cause the angle of diffraction to increase. Okay, so the angle of diffraction is sine theta. We want to see what will make sine theta increase. The first one says decreasing the distance between the filament and the anode. Yeah? So that is just to do with accelerating the electrons, and decreasing the distance between the filament and the anode doesn't make any difference. It's the voltage that decides on the acceleration of the electrons. Decreasing the potential difference will mean that they will reach a lower speed, less kinetic energy, so less momentum. And since the wavelength is h over p, that's de Broglie, the lambda will increase. Okay, so the wavelength will increase. And if the wavelength increases in this equation, the wavelength is proportional to sine theta. So sine theta will increase. So this one is correct. Increasing the filament temperature, that's just emitting the electrons, so it's not relevant to the diffraction. It's before the diffraction occurs. And it's not going to have any effect, really. You'll just make the filament too hot. And using a crystalline material with a larger lattice spacing, so if the lattice spacing is larger, you'll actually get less diffraction because you want it to be small, like the wavelength of the electrons, which are quite small. So if d increases, which is basically what they're saying, then sine theta will decrease because they're on the same side of the equation. If one goes up, the other goes down. So the answer is B. Okay, so this is very good multiple choice for revision. Okay, so we got some from year 12, some from year 13. The next question, question 5, is a particle has a charge and mass. The particle P causes an electric field and a gravitational field because it has charge and mass. The charge causes an electric field and the mass causes a gravitational field. So again, this is unit 5 for the fields, and it says unit 4 as well. So I'm not sure where in unit 4 we're talking about. Oh, okay. Gravitational field is in unit 5, and electric field is in unit 4. Okay? So which of the following statements is correct at a distance r from P? Okay? The gravitational field strength is proportional to 1 over r. So field strength has an equation which is proportional to 1 over r squared. You can find the equations for electric field strength in the back, or gravitational field strength. So G, for example, is equal to Gm over r squared. So it's not to do with 1 over r. This is incorrect. Okay? Electric field strength, E, is proportional to 1 over r squared, proportional to 1 over r. No, both the field strengths are proportional to 1 over r squared, just like there's an analogous equation for electric field strength, which you can look up, kq over r squared. Gravitational potential is always positive. No, that's incorrect. Gravitational potential is always negative. Okay? And finally, it must be D, by a process of elimination. Electric potential is proportional to 1 over r. Yes, this one is proportional to 1 over r. Electric potential is V. V is kq over r. Okay? So the answer is D. 5 questions done. A lot of knowledge gained. Next question. The graph shows how the binding energy per nucleon, that's here, varies with nucleon number, which is here. Okay, for atomic nuclei. The arrows W, X, Y, and Z represent changes in binding energy per nucleon, and nucleon number. Okay, so W is going up towards the peak, X is going away from the peak, Y is going down the slope at the higher nucleon number, and Z is going the opposite direction. Fission and fusion nuclei may result in the release of energy. Basically, anything that goes up the slope, releases energy, because you're making something more stable. If you make matter more stable, it releases energy. Which row of the table, it says, gives the arrows representing energy released by fission and fusion? So fission would be Z, releasing energy because you're going up the slope, making something more stable. and fusion would be W going up the slope, okay? So increasing the binding energy per nucleon will release energy, okay? So we want W and Z, and the only one with W and Z is C, okay? So this is also a Unit 5 question, yeah, for international A-level students, and very common in both sets of multiple choice questions. So again, this paper is 1 hour 45, which is the same as Unit 5, which is 1 hour 45. So the next question looks like it's from Year 12 again. So international A-level students, if you're not retaking Unit 2, this is just good revision for your physics. The diagram shows a ray of light passing through a medium X to Y to Z, okay? The speed of light in medium X is Vx, the speed of light in medium Y is Vy, and so on in Z, it's Vz, okay? So, you can tell by the direction of bending towards the normal, which one is the slowest. If it bends the most towards the normal, it must be the slowest. So Y is the slowest, and Z bends away from the normal more than the original direction of X. So slowest is Y, fastest is X. Yeah, so this is how you work it out, bending towards or away from the normal. Okay? So which of the following shows the speed in order of increasing magnitude? So you want the fastest at the end. So Vz at the end. So these two have Vz at the end. Yeah? And you want the slowest at the beginning. And the slowest is Y. Yeah? So this one is incorrect. It's got X first. So the answer is A. Okay? Question 8. A weight of 2 newtons is suspended from a spring constant of 50 newtons per meter. So that's K. We know K. Yeah? So this is from Unit 1 materials. Yeah? Which is also used in Unit 5 when you've got simple harmonic motion. So there's a link with SHM, because sometimes you've got to work out the spring constant to put it into the oscillations equation. T equals square root of 2, T equals square root of 2 pi m over k. Yeah? Is the simple harmonic motion link. But I don't think you're going to need this in this question. Okay, what is the elastic strain energy stored in the spring? In joules. Okay, so once we know K, we can work it out because we know F. So X is F over K, because we know F and we know K. So we want the answer in terms of F and K. Yeah? Does that make sense? So here we know F. Here we know K. And we know then energy is half Fx or half Kx squared. And you can then replace X with F over K, which I think is probably what I've done. Yeah. And you see I put half K, and instead of X squared, I've put F squared over K squared from here. Okay? So let's just get rid of some of these scribblings. Okay? So you put F over K instead of X squared, and then you can see that it's half F squared over K. Half F squared over K is what we want to simplify it to. Okay, so this goes in there, simplified. Then you put the numbers in, and you see it's half times 2 squared over 50. And that is D. Hope that makes sense. So we did not need to use this equation. So there is a link between Unit 1 and Unit 5. And students doing the linear need to revise a broader set of knowledge than international A-level students, which need a deeper revision of Unit 5. So sometimes because they can do more questions on Unit 5, like this one, they can go into the subject in more detail. Okay, so more breadth in linear, more depth and detail in modular. A mass is suspended from a spring and displaced vertically. So this is simple harmonic motion we're just talking about. The mass performs simple harmonic motion. The graph shows the acceleration of the mass, over a whole oscillation. And which of the following graphs shows how the velocity varies with time? If you got the acceleration for the same time interval, you know that acceleration is the rate of change of velocity. In other words, the gradient of one of the velocity graphs should give the shape of the acceleration graph. Okay? So we want the acceleration at time 0. The acceleration, the gradient should be 0 at time 0, because the acceleration at time 0 is 0. Okay, so we want the gradient at the beginning of the velocity time graph to be 0. Okay, so which ones have 0? This one has a 0 gradient at the beginning. Peak or trough momentarily will be 0. So it's either B or D, because neither A or C have a gradient which is 0. Then you want the gradient to be, as t gets greater than 0, you want the gradient to be positive. So it's going to go upwards. So it has to be B, because here the gradient is going upwards. Okay, whereas here, the gradient here is negative. So this one is wrong. B is the correct answer. Okay? There we go. 9 questions. So both the International A-Level Unit 5 and the paper in Year 13, Paper 2, have 10 multiple choice questions and then structured questions. So the next question is from Unit 1. A wire of length L and diameter D is fixed at one end. A force F is applied to the wire, so we're talking about Young's modulus, and creates an extension E. So automatically I know we're going to do Young's modulus is a stress over strain, or FL over AE. So this is from Unit 1, materials. Okay, so a second wire made from the same material, this time length is doubled, 2L, and a diameter is halved compared to before, and it's fixed in the same way as before, and this time a force of 2F is applied to the wire. So this is just manipulating all of this. So originally the Young's modulus will be FL over AE, because we're just using F, L, E and A, yes? And A is pi d squared over 4. So I've tried to put the numbers in. So this will be 1. And for the second one, we have the E is going to be 2 times the F. So F is 2. I'm going to put it in green. 2F doubled. Double the length. So instead of L, we put 2L. And then it's pi d squared over 4 for the area. And the area is halved. So it's pi d squared over 4 divided by 2 again. So that's going to be over another 4. So 4 is going to go on the top. Okay? That's where the 4 is come into. And the extension 2 is what we want to find out. Okay? Now, because they're made of the same material, these two equations must be equal, can be equated. So you put FL, I see, there's a 4 there for both of them because of d squared over 4, and the 4s will cancel out. Okay, so even in this one, the first one, because of pi d squared over 4, there's a 4 at the top. Okay? So I think I was a bit confused when I was explaining it the first time. There's a pi d squared over 4 for the area in the first case. That's why it changes to the green circle. okay, in the yellow box at the top. And the second one, you got the 4 because of pi d squared over 4, and this time you got d squared, d over 2, half the d, yeah? So another factor comes in, okay? So if you cancel out everything, you will see that these two equations are equal because e is common in both, and you can cancel a lot of the numbers. The 4's cancel, the f's cancel, the l's cancel, and all you're left with is the numbers outside, so the 4f, and you see the 2 inside the bracket on each of them stays. The pi d squareds cancel. There's another 4 at the bottom here, yeah? So we've got 4 at the top, and 4 as a fraction should go to the top, okay? So 4 times 2 times 2 on the top is 4 times 2 is 8 times 2 is 16, shows that there is a ratio of E2 will be 16 times E1, yes? So you put E2 goes on the other side, and you just change the subject for the equation, and you should get D. So there's a lot of ratios involved in these kind of questions, and this is quite common. And it's, for the question 10, they will give you the most work to do. Okay. Remember, if you're finding it to struggle to get these kind of questions done, go and do the structured ones, and then leave this at the end, yeah, to work out the correct answer if you have time left at the end of the exam, because only 1 mark in a multiple choice. Okay, the next question is from Unit 2. So these are short structured questions, 2 marks. So it looks like you just have to use an equation. A student shone green light from a laser through a diffraction grating. So again, it's n lambda equals d sine theta. Yeah, very common question in both exams. And you see a diffraction pattern on a screen. The student determined the angle of the 3rd order maximum. That means with n equals 3. Yeah, they want you to calculate the wavelength of the green light. So you've got to work out lambda when n is 3. And they've told you the angle of the 3rd order displacement is 73.3. So they've already given you theta. And the diffraction, the grating spacing is already given to you. Okay, so it's not the number of lines per millimeter. They've already given you d values. So all you've got to do is plug in all the values, make lambda the equation, and divide by 3 because n is 3. Put the numbers in, and you'll get the answer out. So 2 marks. 1 for inserting all the correct numbers. So one of my students thought that this was the normal value that they give, where it's the number of lines per millimeter. So often they give you a number of lines per millimeter, and you've got to work out D. In this case, you don't need to do that because it's given to you already. This is D. Okay? So be careful. All right, so the mark scheme is here. There's the multiple choice. Okay? So you can stop the video if you want to look at the mark scheme. And there's 8, 9, and 10. And there's the question we just did. Okay? And then these are all the equations. You get an equation booklet. Yeah? Whereas in the IAL, it's just the data sheet comes at the back of the paper, so it's a slightly different style. And you don't need to return the booklet with the exam paper when you do the linear exam. Okay? So I thought it'd be worth seeing. It's the same data more or less, except they use 2 columns, so you can see you've got mechanics stuff there from Unit 1, and then you've got 2 columns of equations, whereas in the IAL it's a single column of formulae. Okay, then you've got electrical circuits, waves and particle nature, yeah. So all these equations, you can look down. Then you've got the materials section, again from Unit 1 of the IAL. Then you've got further mechanics, which is Unit 5 of IAL. All the capacitor equations, yeah. That's, I just want to see, there's one thing in, this. And this, lenses, is not in the IAL. Okay, so it's only in the linear. So this is not in IAL. That's the only difference in content. Oh, and they also give you these equations, which are sometimes useful in IAL, and I have seen questions which want you to know this kind of knowledge, but they give it to you they don't give it in IAL, so not given in IAL. That's the other difference. Okay, and then you'll see the rest. These are Unit 5. Okay, the rest is all Unit 5. Yeah, and that's the end of the data and the relationships. I just thought it'd be useful to compare. Next question, question 12, is from Year 12. So if you're doing IAL, not retaking Unit 2, then you can skip this question. This is the photoelectric effect. It leads to observations that cannot be explained by the alternative theory, the wave theory of light. When ultraviolet is shone on a charged zinc plate, electrons are released because ultraviolet has a higher frequency. So its frequency is higher for ultraviolet. Okay? When visible light is shone, electrons are not released because the frequency of ultraviolet is higher than it is for visible. Ultra means high. Okay? State what's meant by the threshold frequency. So the threshold frequency is the minimum frequency required to get enough energy to equal the work function. Okay? So it's the minimum energy needed to get an electron to the surface, but you need to be above it to release electrons. So the energy required must be HF must be greater than HF naught, that's the energy of a photon, to release electrons. Okay, so I think that's quite a tough question for 1 mark. So phi is the work function, and phi is the amount of energy required just to get the electrons to the surface, and then you need a little bit more to give the kinetic energy. Okay, so remember the equation is HF comes in, minimum work required is phi, and anything extra goes into kinetic energy of the electrons, and they're called photoelectrons. All right, so that's a crucial definition that you need to be aware of. Explain why the observation of a threshold frequency is not consistent with wave theory, with the wave theory light. In other words, why can't wave theory explain this threshold frequency? Because in wave theory, energy is not related to frequency. Yeah, in that, and I'm expanding on this. With waves, any frequency would lead to a sufficient build-up of energy over time. So if you waited long enough, the waves are just continuously coming, and energy will be dependent on time rather than frequency. Yeah, so it won't be sufficient to release an electron, or should be sufficient over time. I'm saying it should be sufficient over time to release an electron eventually. Yeah, and this is not observed. So because it's not observed, it means that the wave theory of light cannot explain the concept of threshold frequency. Yeah, it's not observed that electrons are released with any frequency, okay, or with any wave. So then the next question says the photoelectric effect can be explained using the idea of photons. So photons, the energy of a photon is E equals HF, where H is Planck's constant. So they want you to know what is meant by the term photon. A photon is a quantum, which is a discrete packet, yeah, of electromagnetic energy radiation. Okay, so radiation is a form of energy. It's electromagnetic in nature, and it comes in discrete packets, and the size of the packets is given by this equation, E equals HF. Okay, and that's your 4 marks. So it's a good revision for those of you retaking any modules from year 12, if you're doing the international A-level, and if you're doing the linear, you need to know all your stuff from year 12. So next question is astrophysics. So it's from Unit 5. So Aldebaran is a red giant star. For a black body radiator, which is a theoretical understanding of how stars obey the black body radiator's rule, yeah, the surface temperature and the wavelength at which the intensity is maximum is given as this. So the maximum wavelength is this value. So the peak wavelength emitted by this star, which is a red giant star, is 7.43 times 10 to the minus 7 meters. Okay, so there's an equation which is called Wien's law, which if you know the lambda max, you can work out the temperature, because lambda max times temperature always gives you this value, okay, which is given to you in your data sheet. And you can work out what the units are. I just haven't put the units in. They want you to determine the luminosity of Aldebaran. So first you can work out the temperature, and once you know the temperature, you can then use the Stefan-Boltzmann law, which links the luminosity to the surface area of the star and the temperature to the power of 4. And again, this is the constant, the sigma, which is given to you in data sheet. So that's why they're giving us the radius of Aldebaran, I don't know how you say it exactly. So once you know the radius of Aldebaran, you know its surface area is 4 pi r squared, yeah, because it's a sphere. That's the surface area of a sphere, 4 pi r squared. And if you put the numbers in, you will see, according to the mark scheme, the surface area will be 1.24 times 10 to the 22 meters squared. Once you know the area, and you also have worked out the temperature using Wien's law. So you found the temperature using Wien's law. You then use the Stefan-Boltzmann law with the temperature in it and the surface area to find the luminosity, which is given by this equation. So you put all the numbers in. Here it is. You get all the numbers in. That's the constant which has been given to you here. There's the constant that we just looked at, 5.67. 4 pi r squared. So the answer, this would be 1.24 times 10 to the 22. Okay, so that is this. I've just done it all in one go here. And then temperature, don't forget to put it to the power of 4. One of my students did everything right, but forgot to put the power of 4 in and lost unnecessary marks. Okay, and the answer has been given to 3 significant figures, because the data is provided to 3 significant figures. That's another 4 marks done. A good revision of Wien's law and the Stefan-Boltzmann law. Okay, there's the mark scheme. Question 12, which we looked at before, about photoelectric effect. You can stop the video, and this is the question we just did. Question 13. Okay, going to do one more question, and I'm going to have a pause. Go and get something to eat. Okay, question 14. A student used 2 converging lenses in a combination to form an image of an object. So now, this is from year 12 content, but it's not in the international A-level, because optics, as in lenses, is only studied in the linear. Okay, so linear only. And they want you to show that the power of the combination of lenses is about 20 diopters. Okay, so that's the power is in diopters. So the focal length of lens 1 is 10 centimeters. You should put it in meters. And the second one lens is 15 centimeters. So we know 0.15. And to get the power of a lens, all you've got to do is use power is 1 over focal length. So it's not that complicated. So the first one is 1 over 0.1, so it's 10 diopters. The second one is 1 over 0.15 in meters. So this gives you an answer of 6.15. Yeah. 6.7, I don't know. So 1 over 0.15 is 6.7 diopters. And the total power, you just add the 2 powers together, if they're in a combination. So you get the answer 16.7, yeah, which is approximately 17, yeah, which that's to two significant figures, which is approximately equal to 20 diopters to one significant figure, okay? So you're rounding it up to the nearest 10, okay? So some students might get confused because they're 3 away, but to two significant figures will be 17, and to one significant figure that rounds up to 20, okay? The next part of the question says the object was 4 centimeters in front of the combination of lenses, and the object distance is given as u, yeah, and you should put it in meters, SI units. Calculate the image distance. The image distance is v in these equations. The equation is 1 over u plus 1 over v equals 1 over f, okay? And remember, 1 over f is also the power of the lenses. So we want to find a v, so we change the equation round to make 1 over v 1 over f minus 1 over u, yeah, and we know 1 over f is the power, so that's that. Take away minus 1 over u, where u is 0.04, yeah, so that goes into this part of the equation, and so you're 16.7 the power. Take away 1 over 0.04 gives you a negative answer, okay? And that means something about where the image will be, and we'll go into that in the next part, okay? So if you do 1 over 1.83 to get v, yeah, so you inverse it, you'll see that it's 0.12 meters from the lens in the negative sense. So let's see what that means. So it says the object height was 1.4 centimeters. So first they do object distance. Now they want you to calculate the image height. So the magnification is either image height over object height, yeah, or image distance over object distance. And we know the image distance and the object distance because it was 12.24 centimeters, yeah. So we know it's 3, and then we know the image height. So you can equate these two equations for magnification. So it's basically ratios, and you'll get the image height is 3 times smaller, 3 times larger than 1.5. Sorry, I'm saying it the wrong way around. Object height was 1.4, it's magnified 3 times, so the image height will be 4.2 centimeters, and that gets you your 3 marks. You can have a look at the mark scheme in a minute. So the object is magnified. Yes, we know. We just worked it out. It's 3 times magnification. State 2 other properties of the image. So we know it's virtual because the answer was a negative value for v. Okay? And we know it's upright because it's on the same side of the lens as the object. So when that happens, it's basically you have a magnifying effect like a magnifying glass. Okay? So I hope this makes sense for your first lenses question if you are doing international A-level. Yeah? And this comes up mainly in year 12 linear. Okay, so I'm going to stop there, take a pause, upload this, and then come back and do question 15. Let's have a look at question 15. So it's about oscillations, okay? So it actually links Unit 5 and Unit 2 quite well. So we'll come back and do question 15, yeah? So if you found that useful, I'm starting to do these linear papers because now I have linear students as well as modular students. So give it a thumbs up and share it with anyone who you know is doing linear in other countries or in whichever country you're in. That would be great to help spread the word that we're now also specializing in linear as well as modular. Okay, so hopefully catch you in the next video. Bye for now.